Things like wings, fins, sails, vanes, and propellers are all just long, flat pieces of material, and when you give them an angle to the airflow, they redirect the air around themselves, changing its pressures and directions. The straight line between the leading and the trailing edge is called the chord line, and the angle between that line and the relative wind direction is called the angle of attack. The greater the angle of attack, the more aggressively the wing redirects the air, up to a point where the wing will stall. A misconception is that airfoils are a requirement to create lift, and they do so simply by their shape. This is not true, or else how would my flying sheet of foam board fly? Airfoils are, however, optimized shapes, which are designed to do their job the most effectively and efficiently. Asymmetric airfoils with camber do actually create a little bit of lift at zero angle of attack. You have to reduce the angle of attack a little bit more to what's called the zero lift line to achieve zero lift. I thought about a couple of ways I could measure the angle of attack, and I thought about electronic data logging with two pitot tubes at different angles, and I thought about mechanical systems like the one used on the CRJ-200 that I recently flew on. But then I thought of an easy, fun, and visual way to see and roughly measure the angle of attack. So I drew and 3D printed this thing to be mounted on the leading edge of my big wing. It fits two bearings at the end, and I put a shaft through those. I printed this big degree wheel to adhere to the arch, and I calibrated it to the 10-degree knobs that I designed into the part. And then I put this little wind vane onto the shaft so that it always shows which way the wind is coming from. As you can see from this wind tunnel picture, the wing in subsonic flight is actually already bending the air in front of it even before it gets there. In order to try and avoid this upwashing air, I designed the angle of attack indicator to stick up and out as far as practical. I also put some telltales on the top of the wing so I could try and see at what angle the wing stalls at. What I found is that my wing doesn't actually just break into a sharp stall all at once at the same angle every time. This challenged my understanding of a wing stall and what the critical angle of attack actually is. I also 3D printed some vortex generator strips to install on the wing, and interestingly, I didn't actually see any improvement despite my previous experiments being very successful. One viewer of mine sent me some golf ball dimple sheets to try also. I hope you enjoyed that, and thanks for watching. Neat. Neat. Wow. Neat.